Okay, good afternoon. So next week's homework will be due the Monday after President's Day. So I'm not going to have anything due next week, but I will have an assignment that's on the material that we're doing right now. Okay. So I'll post that on BSpace today. But like I said, that'll be due a week from Monday. Okay. And there'll be 2 homework assignments due then, but you should probably want to do one this week. Whoops. But you just won't hand it in until the week after. Okay, any questions about that? About anything else? Okay, so it's a reminder that I guess I've forgotten. Reminder for myself that there's a change in the syllabus. I still haven't posted the revision, but the syllabus the original syllabus says there's a quiz due also on President's Day. The quiz will be posted on President's Day, but due the following Monday. Okay? Questions? Anything? Okay, so last Thursday I just started chapter 10, regression, a little bit, talked about the main idea, and I'll go back over a little bit briefly, quickly, what I did last Thursday about chapter 10. We'll start with the picture, and I'll draw this picture in terms of the example that I'm going to do. So the example is with midterm and final scores. So suppose we have some big class, average midterm score is 71 points, SD is 12, and final scores have an average of 70 and an SD of 11. And the correlation between midterm and final scores is 0.6. So I'll present a problem, but before I do the problem, I want to kind of talk generally about regression. But the general kind of problem here, this sort of standard problem we'll ask is something like predict final score for someone who got 83 on the midterm. So that's the general kind of question we're trying to answer in chapter 10 is to try to predict y variable final score from the x variable midterm score in this case. One way you might think about this prediction process, I've tried to say this in different ways a couple times. A good prediction would be the average final score corresponding to everyone who got an 83 on the midterm. So another way to think about this is that you want average final score for everyone who got '83 on the midterm. And what regression attempts to do is to find this. Okay, try to find that point. So if we draw a picture for this, midterm score is on the x-axis, final score is on the y-axis. And I'm sorry, I want to say along here also that the scatter diagram is football shaped. Okay, I'll talk a little bit more in a minute about why that's important. Okay, there's my picture, football shaped scatter diagram. So just to remind you of some landmarks, this point, 71 on the midterm, 70 on the final, is often referred to as the point of averages. It's just the average x is the x coordinate, the average y is the y coordinate, point of averages. Okay, so the graph of averages gives you the average y value corresponding to each x. So essentially, what we'd like to know is what those points are. And I'll draw this one over 83. Okay, so this is the point we actually want. I'm attempting to draw it halfway in between, so it's like in the center of that strip. So if you think about all 83s on the midterm, that's roughly what their average should be. So that's what regression is attempting to do, is to find that point. Now, I mentioned before, this is not, in general, perfect. Data is a little bit irregular. The points here will be scattered all over the place. It doesn't really look like this nice shape. Since the points are scattered all over the place, the actual average value corresponding to each x, those average values corresponding to each x are called the graph of averages, and they're not quite on a line. They should be quite close. But just because data is not sort of perfect, there's no law that says the people who got that 83 on the midterm have to get that exact average as their the average of their final scores. It might be off by a little bit. So this is called the graph of averages. And what I said before is that the regression line is a smoothed version, or a smooth version, either way. Regression line is a smoothed version of the graph of averages. OK, so like I say, in general, the graph of averages should be close to a line, not necessarily exact. What we'd like to do is find the average y corresponding to these x's, and the regression method will do a pretty good job. It'll find a point on the regression line. Okay, so just as a quick aside, well, never mind. I'll do the aside later. Sorry. Yeah, so the regression line roughly follows those points. So we'll call that the regression line. And like I say, I've drawn it so that they're really pretty close to a line, but it doesn't have to be perfect. OK, so any questions about the kind of big picture going on here? OK, so how do we do it? The regression method I wrote up last time, just quickly. First step is to convert x to standard units. Second step is to multiply by r. And that multiplication gives us a predicted y value in standard units. Okay, once we've done those first two steps, what we have there is the predicted y value in standard units. And the kind of extended example I did with predicting foot length from either GPA or height or shoe size was an attempt to illustrate this. It was an attempt to illustrate that if you are 1 SD above average for whatever the x variable is, right? So when we do the first step, convert x to standard units, suppose we get 1. We got someone 1 SD above average. Well, your predicted y value should be r SDs above average. So if you are 1 SD above average to start with, say r is 0.6, like in this case, you should be predicted to be 0.6 SDs above average for y. Now, if the correlation is quite close to 1, start with something 1 SD above average, your prediction should be quite close to 1 SD above average. If your correlation is quite close to 0, then no matter what you start with, when you multiply by r, your prediction is going to be quite close to 0 in standard units, meaning approximately the average is your best guess. So if you start with like a GPA 1 SD above average, multiply by 0 or something very close to 0, that means your predicted foot length would be quite close to the average of everyone's foot length. Okay. All right. So finally, once you get that predicted y value in standard units, last step is to convert out of standard units. So the math here is, pretty much what you're used to. Converting into standard units and converting out of standard units is something we started doing in chapter 5. And then multiplying by r is just, multiplication. So these are all steps that mathematically should be fairly straightforward for you. But yeah, the whole process and the whole intuitive idea is fairly complicated. I don't know. There's a lot to it. There's a lot to say about it, at least. OK. So let's do it. For my example, as I stated that problem there, so in my example, I start with an x value, a midterm score of 83. So we're here, 83. So step 1, regression method is to convert that to standard units. And I chose that just because it comes out nicely. 83 minus 71 over 12. Its value minus the average midterm score divided by the SD of midterm score is just 1. So in fact, we are starting off with someone 1 SD above average for midterm score. Multiply that by r. And again, this is the predicted y value, the predicted final score in standard units. So when you convert that out of standard units, you can think of this as a formula if you want. Maybe in chapter 5, you know how to convert standard units into a value. I just kind of usually think about this in English. This means 0.6 SDs above average. So 0.6, and it's for a final score, right? So 0.6 SDs, that's the final SD, plus the average of the final scores is 70, gives me a final score of 76.6. OK, so that's my prediction. If you want to go back to the picture, that's this point here. OK. Right. OK, any questions about regression method? How to do that bit of math? Yeah? Does the regression line have to pass through the point of averages? Yes. Yeah. So one way to think about that is if you, this method will give you points on a line. Anytime you choose a different x value, go through this process, you're going to get a point on the regression line. And one way to see that the point of averages is always on that line is to think about what would happen. If you take a value of 71 and predict y, well, convert 71 into standard units. It's 0, right? It's right at the average. 71 minus 71 over 12 would give you 0. Multiply by r, you still get 0. That means the predicted y value is 0 SDs away from average, so you would get the average there. Okay? So if you have the average here, you must predict the average of y there. Okay? For these points here on the graph of averages, they might not be quite exactly right. Okay? So there's a little bit of I don't know, that idea you should be aware of, that we're not going to necessarily do things perfectly, but we often talk about, kind of finding the average y value corresponding to the x, to this x, and using the regression method to find that point. Well, technically, we're not actually finding that point. We're estimating that point. We're estimating what that value, what we expect that value to be. It's not necessarily exact. OK. Other questions on that? OK, so let's see. OK, so I want to do the same process, the regression method, in a slightly different context. I'm going to still deal with the same data, but I'm going to start with someone who is at 76.6 on the final. So suppose that's a possible score. Okay, so suppose that's a possible score. Let's suppose we want to predict that person's midterm score. Somehow we know their final score. We don't know their midterm score. So any thoughts? Is that going to be, is the answer going to be 83? No. Why? It's not 83. You might think it should be 83. Sorry? Was that? Yeah, when you predict back the other direction, you're going to multiply by r again. Okay, you're not going to divide by r. So let's think about what's going on here. So if we now treat this as, I'm just going to draw a quick sketch. I'm not going to draw out the nice, a completely big picture. But if we think about this, we have 76.6 here. Now, if we think about predicting midterm from final, we're thinking of final as being the thing we're predicting from. We have to kind of go through the same steps that we would have in the other direction. So what we're going to do is we're going to convert to standard units, multiply by r, and convert out of standard units again. So 76.6, we actually know in standard units it's 0.6, right? If we convert this back into standard units, we're going to get 0.6. But then we're going to multiply by r again. So first step, converting to standard units. I'll write down the math, but kind of know the answer here. Minus 70 over 11 is 0.6. And then we multiply that by 0.6 to get 0.36. And now 0.36 times the SD for midterm scores plus 83. Find that. Did I do that wrong? I'm sorry. The average there should be 71, right? Now that, oops, sorry, lost it, is 75.3. Okay, so it's still a little bit above average, but it's kind of low compared to the 83, right? Okay, so I wanted to just quickly illustrate this idea that you can't predict back the other direction. Okay, I'll come back to this idea a little bit, but this is an example of what's called the regression effect, or regression to the mean. And essentially, it's this idea that your predicted value should be closer to the mean, meaning smaller in standard units. And it's because of this multiplication by r here, right? We started with something that's 1 in standard units. Now our predicted value is only 0.6 in standard units. Here, we start with 0.6 in standard units. Our predicted value is 0.36 in standard units. So this multiplication by r means essentially that the predicted value is getting closer to 0 in standard units, closer to the mean. Now remember, r is always between -1 and 1, so that has to happen. Anytime you multiply by r, the result will be smaller. It's possible it reverses sign if r is negative, but still, absolute value should be closer to 0. Okay. Okay. So I'll come back to that idea in a few different ways. I wanted to at least do the math now. So any questions about that? Okay. So I want to do a different example. Suppose we have this information that the correlation between math SAT scores and Stat 21 grades. And I'll say grades as a, I don't mean as a letter grade, I mean like the total points. So like the total points you get in the course, oops, is also 0.6. And we have a football-shaped scatter diagram. and one person is at the 31st percentile on the MSAT. Okay. And I mean this just as, obviously, this data only makes sense for people that took or taking or something Stat 21. So yeah, this is 31st percentile on MSAT of the people that have Stat 21 grades. Okay, and now I'd like to ask this. So what is a good guess? What's a good guess for that person's percentile rank in Stat 21? So first of all, can I answer this question? Any thoughts? Yeah. So he's supposing that he thinks you can answer it if we assume that both of these follow the normal curve. Yeah. And he's suggesting that we probably need to know what the average and the SD are if we're going to do this. Any other thoughts? Comments? Yeah. So there is a little bit that I'm not telling you. And I haven't defined football shape yet. So let's do that first, and then I'll get back to the example. I'm not going to fully define football shapes for now, but I want to at least tell you what's relevant for this chapter. There's more that I'll tell you once we hit chapter 11. For now, football shaped means three things. First is that the relationship is linear with no outliers. Second is that both x and y follow the normal curve. And third, I'll write down the word and I'll just say what it means very briefly. This is not relevant for us until we hit chapter 11. The word is homoscedastic. What it means, just very quickly, is that for each x value, y has the same spread. You don't have to think about that yet. Spread, you know, is sort of measured by standard deviation or something like that. So basically it's saying that if you got an 83 on the midterm, the spread, for all the people that got 83 on the midterm, the spread of their final scores is the same for all the people that got 71 or whatever. If you want to think about height and weight, it means that if you put all the people that are 6 feet tall, the spread of their weights would be about the same as if you put all the people that are 5 foot tall in a room. Okay, that's what this word means. Okay, but yeah, we'll talk about that more in chapter 11. So this is where I wanted to have my little aside. So linear means that the graph of averages roughly follows a line, is one way to think about it. If that didn't happen, regression would not do a very good job. So if we had something that looked like this, for example, okay, what regression would do is it would try to do this. And the average y value corresponding to each x value is not going to be very close to that line. If you consider like x value here, average y value is about there, not particularly close to the line. You know, out here, not very close to the line. So it's not so good, right? So regression, not such a great idea if you have something that's nonlinear. If you have something that's linear, those points, the graph of averages should follow the line. These are points on the graph of averages. If it's linear, then those points should follow the line, and that line is the regression line. Similarly, for if there are outliers, doesn't work so well. And I don't know, maybe that's, if I just draw a few points here, maybe that's pretty clear. Let's draw something like this. So if this is up here, the regression line is going to attempt to go through those points, sort of go through the center of those points. And if you think of a vertical strip here, the regression prediction would be down here, it'd be too low. Up here, so not so good, right? So the average in the graph of averages, again, does not follow a line so well. OK, so that's a little bit about 1. 2 is what's relevant for this problem. So as the first person said, we need to know this in order to do this problem, OK? So if this is true, x and y follow the normal curve, and it is, since I told you it's football shaped. Let me leave that for a bit. Think about what the regression method says. First step is to convert x to standard units. Well, if I know that, and I'll number this in the same way. Step 1 is convert to SU. If I know that x follows the normal curve, I know that this person at the 31st percentile is about here. Okay, so this area is 31%. So this is that person's value in standard units. I can find that because of symmetry here. We have 31% here, about 38% in the middle. And it turns out that this is about minus 0.5. Okay? So I don't actually care about what the person's actual MSAT score is. All I care about is what is in standard units. So if it follows the normal curve, I can do that. 31st percentile, 0.5 SDs below average. Second step is to multiply by r. So I get minus 0.3. And what's the third step? The third step is to convert out of standard units. Well, I can't convert into a number of points for stat 21 or a grade or anything like that, but I can convert into percentile rank. Okay? So I can use the regression method to guess the person's percentile rank in stat 21 with the same idea. If I'm going to guess, remember this is the predicted y value in standard units, so around here is minus 0.3. Look that up on the normal table. And it's 23.58 in the middle. So this is about 24. 24 there gives me about 38% here. OK? So my predicted percentile rank for this person would be 38th percentile. OK? So that might seem, I don't know, depending on how you think about what regression is doing, that may or may not be surprising. I think a lot of people looking at this problem might have just thought in their heads, well, I don't know, if they're 31st percentile for MSAT score, maybe you'd think that there'd be 31st percentile for stat 21. And again, what's going on here, similar to the previous problem, is that the multiplication by r step gets us something that's closer to the average. We started with standard units of minus 0.5. Multiplication by r gives us a predicted y value that's a little bit closer to the average. OK? And in percentile terms, that's also true, right? We started with 31st percentile. 38th percentile is a little bit closer to the average. In this case, the average is the same as the median, 50th percentile. OK. Questions on that one? Yeah? Yeah, good. So if the correlation were 1, then your predicted percentile rank would be 31st percentile. OK? So yeah, if it's actually equal to 1, then this second step doesn't make you any closer. It just leaves it the same. What's going on if correlation is 1? If correlation is 1, then all the points are on a line with positive slope. So not only is that your predicted value, it's your actual value. If all the points are on a line, then if you got 31st percentile for MSAT scores, you must get 31st percentile for Stat 21 grades. Okay, all the points are on a line. You can just read off the line what everyone's Stat 21 grades were. Okay, so that'd be sort of extreme. It's sort of unrealistic in this case to think that it would be 1. Okay, any other questions? Okay. Okay, so let's get back to this intuitive idea. Where am I? Okay. So I mentioned the words. I didn't quite write them down. The regression effect. Okay, these are just two terms for the same thing. The book calls this the regression effect. I slightly prefer the term regression to the mean because it's more descriptive of what's happening. Your predicted values are getting closer to the mean. Okay, so that's the idea behind it. So this says that than the value started from or predicted from. And this is for correlation between -1, strictly between -1 and 1. So again, if R is actually equal to positive or -1, then the predicted values will be the same distance from the mean. If R is +1, the predicted value will be exactly the same in standard units. If R is -1, the predicted value will be the same distance, just in the other direction. Okay. Okay. So questions on that idea? What that means? Okay. So let's talk about intuitively why you might think that that would be true. So. So Yao Ming is my, I don't know, maybe most famous, very tall person. Shaquille O'Neal maybe is another example. This would work if you want. So Yao Ming is about, I think he's about 7'5", 7'6". Let's suppose that Yao Ming has a bunch of sons. Okay. So would you expect his sons to be, on average, as tall as he is? If you had to guess. Probably not, right? So what's going on here is an example of the regression effect. And I think it's a little bit, the regression effect is a little bit easier to think about with extreme cases. For example, if I go back to this midterm final example, if you got an 83 on the midterm and you are 1 SD above average, and I told you, well, I think you're going to do about 0.6 SDs above average on the final, you might be a little bit insulted or hurt that I would think that I would expect you to do worse on the final than you did on the midterm. Might sort of not seem fair, maybe. Well, the thing is that it's not true that everyone gets closer to the mean in general, but there should be a tendency that way. And I think, like I say, it's a little bit easier to get your head around if you think about extreme cases as to why that might be true. If we think about all the sons of everybody, like everybody, say Yao Ming's age or something, just all the sons that are born around the same time as Yao Ming's sons, maybe somewhere in the world there will be a few people that are over 7 feet 5 inches tall, okay? Where do we expect those to come from? Probably not from Yao Ming. Probably those sons, those very tall people in kind of the next generation, they'll have tall fathers, but there are very few people like Yao Ming around having kids, and so there are not very many opportunities to produce an exceptional case like that again, right? So one way you might think about that is that Yao Ming not only has like very tall genetics, very tall genes, but he maybe got lucky in every conceivable way you could think of to manage to be as tall as he is, right? Everything that went into making Yao Ming was sort of as tall as possible, right? Like what he ate and whatever things, like the mother's DNA, the father's DNA, everything that went into Yao Ming suddenly somehow was like unusual, right? And there are lots and lots of babies being born all the time. There are lots of opportunities to produce such an unusual child, but probably didn't come from the very few people in the previous generation that are as tall. So when you think about Yao Ming's sons, why are they not as tall as Yao? Well, maybe they didn't get everything to work out just right to be so tall. Okay, I believe his wife is a member of the Chinese basketball team, and she's also quite tall, not as tall as he is, but sort of in amongst women, she's also exceptionally tall. So that helps, right? On average, you might think that Yao Ming's wife, if you had to guess, you probably guess that he'd marry someone tall, but maybe not, very, very tall. In general, taller men on average marry taller women. There's some correlation there, but not necessarily as tall as them. That's another example of what's going on with the regression effect. Okay, so his sons, tall. You should expect them to be tall. But on average, not as tall. Okay? So this basic principle works for the midterm scores and final scores too. If you get one SD above the average on the midterm scores, you expect to get above average on the final scores. But on average, all the people that get one SD above average on the midterm, on average, they're a little bit closer to the mean. Okay? So if you want to think about extremes in this picture, think about out here, the person who does the very best on the midterm, well, you don't expect them to necessarily do very best on the final. On average, they're going to do above average, but not quite if they're not here, right? This point, and again, there's a lot of variability here. It's possible that you'll have a point up here, that the person that got the best score on the midterm also manages to get the best score on the final. But typically what will happen is that out of all the people that are kind of getting good scores on the midterm but not the very, very best, out of all these people, one of them will manage to get lucky or study exactly the right material or whatever, and that person will end up getting the best score on the midterm instead of the very best person on the midterm the first time. So there are that person. You might think of that person competing against everyone else in the class, right? Who's going to get the best score on the midterm? Might be that person, but it might be that out of everyone else in the class, someone else will manage to get the best score on the final. Okay? All right. Questions on this general concept, regression effect, regression to the mean? Okay, so you can see how the math works. Hopefully you can see a little bit intuitively of how it works. I want to do another example that kind of addresses this idea, but let's first take a break. Okay?
What if it worked out?
Okay, let's get started again. So I wanted to do another example. This is kind of mathy. This is in your book, but the first time I read this in the book, it didn't really quite make sense to me. So I thought, but then once I did kind of get my head around what the example was trying to illustrate, I felt like I had a little bit better understanding of what the regression effect was all about. So I thought I'd do it. I'm doing a very similar example to the one. So if you read the book, you'll recognize what I'm doing. If you haven't read the book, then when you do, or if you do, you'll recognize it being similar, I think. Okay, so suppose we have what I'll call true IQ scores. Any questions, by the way, before I jump back in? Actually, someone brought up a question that I thought I'd maybe just show you on the picture. I'll get back to this idea, I guess, again later. But this 75.3, why is this not 83? One way to see this geometrically is just to think, well, when you predict y from x here, the 76.6 just visually looks like it's right about halfway in between there. Well, just visually, 83 does not look like it's the average midterm score for everyone who got a 76.6 on the final. Right? Think about the midterm scores all along here. 83 doesn't quite look right. That would not be a very good prediction of the midterm score based on the final score. The actual value in the picture is probably somewhere around there. I'm trying to find about halfway in between there. So that point is the 75.3 in my calculation. Okay. So if you want to just think about visually, what's going on there, that's one way to think about it. And if you imagine, well, let's leave it at that. I'll talk about this a little bit more at the very end of lecture. But yeah, so I just wanted to, while that picture's up here, mention that. Okay. So any questions about any of this so far? Okay, so let me get into this example. Let's suppose we have what I'm going to call true IQ scores. Well, and I shouldn't say scores. True IQ values or something. This is what I think of as kind of a number embedded in your brain somewhere that we have no way of seeing directly. Okay, there's some true IQ in there, and for everyone, the average of the values is 100. Standard deviation is 15, and they follow the normal curve. Now let's suppose that we give a bunch of people a test. So IQ test. And your score on the test is equal to your true IQ plus or minus 5. And you can think of that plus or minus 5 as just being random. This is not really realistic. Okay, this is not how you would expect to score on an IQ test, I don't think. But just whatever your true IQ is, your score on the test is exactly whatever your true IQ is plus or minus 5 points. So, like I said, you can think about this as just like a coin flip. Half the people get 5 points added to their true IQ. Half the people get 5 points subtracted from their true IQ. So let's suppose you have a bunch of people that have a score of 125. So take everyone who gets 125. Okay, so what are those people's true IQs? If you got a test score of 125, what's your true IQ? It has to be 120 or 130, right? So these people have true IQs of 120 or 130. So do you expect more of them to have 120s, or more of them have 130s, or the same? Okay. So do more of them have true IQs of 120? Are there more 130s or same of each? So just to make you think about it a little bit, I'll make you vote. So who says more 120s? Who says more 130s? Who says same? Okay. So it is more 120s. And just mostly I don't care if you're right or wrong. I just wanted to make you think at least a little bit about it. Anyone want to say why? So it's right, there are more 120s than 130s. Why is that? Yeah. Is there a hand? Yeah. Yeah, that's basically right. So more people in general have a 120 IQ than a 130 IQ. So if you think about, and I'm going to kind of discretize the picture here. Just imagine there's a bar over 120. It's like the discrete values for the scores. And there's a bar over 130. The percentage of people in this bar, in the bar over 120, is going to be bigger than the percentage of people in 130 in general. Okay, now let's think about who gets the test score of 125. Well, about half these people and about half these people. Half the people in each of those bars should get a score of 125. I'll just kind of shade half of them, right? Half of each of those bars, suppose shaded people get a score of 125. And pile them all together, and you're going to have more 120s than 130s. Okay? Alrighty. So let's suppose we take all those people and we give them a second test. Okay, so give the test scores, I guess I'll write it out. Give the people who got 125 on test a second test. With the same rule, okay? Your score is equal to true IQ plus or minus 5, okay? So now what scores should you expect to see? So you take all these people, in a room, they got a 125 the first time, and then we give them a second test. It's sort of the same style of test. Your score is going to be equal to your true IQ plus or minus 5, but it's like separate from the first test. So just kind of imagine the same test, but with different questions or something. Okay, so what scores do you think we'll see? What are the possibilities? Yeah. Yeah. Okay. So the people in the room, they all got scores of 120 or they all have true IQs of 120 or 130. So when you test the 120s, they either get 115 or 125. When you test the 130s, they either get 125 or 135. So is the average equal to 125, less than 125, or bigger than 125? I'll make you vote again. Think about it for a second. So who says equal to 125? Who says smaller than 125? And bigger than 125? Good. So it's smaller than 125. So anyone want to say why now? Why is it smaller than 125? Yeah.
Since there are more people with a true IQ of 120, there'll, say half of them get 115 or so. There'll be more 115s than 135s.
Yeah, good, right. Okay, so he's basically saying, like we said up there are more 120s than 130s in this room. Not in this room, but in this room. Since we have more 120s than 130s, the 120s, half of them get 115s, half of them get 125s. The 130s, half of them get 125, half of them get 135. So if you imagine sort of trying to balance at 125, it's not going to balance there because there are more 115s than 135s. Sort of, disregard the 125s for a second, but half of the people with true IQs of 120 got 115, half of the people with true IQs of 130 got 135. Since there are more more 120 true IQs in general, the 115s are going to be more. Then there are more 115s than 135s, so the average overall should be less than 125. Okay, so if you didn't sort of see all this stuff behind the scenes, that might be a little bit surprising if you took everyone that got a 125 on the test and then retested them and the average scores were less than 125, right? So I think that might be, if you didn't know anything about statistics or anything else, you might be a little bit surprised by that if you took everyone that got a 125 IQ test score, tested them again, and their averages have gone down, right? This is an example of the regression effect, and the reason why I like this example is that it makes it kind of transparent that the only thing going on here is I've thrown in this little plus or minus 5 here. And all the plus or minus 5 is sort of fair, right? It's equally likely to go up or down, but that little bit of randomness is enough to induce the regression effect, okay? So if there's a little bit of randomness that's kind of equally likely to go up or down, like, with test scores or with heights or whatever, a little bit of randomness like that will make the regression effect start to happen. Now, in real life, it's not this simple, like a plus or minus 5 little bit here, but you can think that, your final score maybe in a class is some combination of your inner ability, like true IQ, including, maybe how well you're prepared and stuff like that, but there's also maybe a little bit that you might consider to be luck. And the luck part you might consider to be, does something happen randomly that disturbs your sleep the night before or not? Or does the questions that are asked on the test might sort of correspond really well with what you know, or they might tend to be things that you happen to not know as well, okay? So there's anything like that you can sort of consider to be a little bit outside of you, that's maybe a little bit random, could make things go up or down. So if you imagine the person that got the very best midterm score, that's someone that undoubtedly was well prepared and studied well and whatever, maybe they're smart, whatever makes up a good midterm score. But they might also have been a little bit lucky in the sense that if different questions had been asked, maybe they would have missed something. But those questions that did happen to be asked on the midterm, they got them. Maybe they slept particularly well, or whatever it happens to be that makes your midterm score good. You might think of it as being sort of somewhat random and somewhat not. And not only did the innate ability or whatever work out for that person, but also whatever happened to be random worked out for them. Same thing with Yao Ming's height. Everything that possibly could have made him tall kind of worked to make him tall. His sons probably won't have every little bit of random thing that might go on make them tall, okay? So that's one way of thinking about the regression effect, is that because of this little bit of randomness, the very high X values are in some sense a little bit lucky, right? If you think about the people in this room that got a 125 test score, you might think of them as on average lucky, Another way to say that, another way to think about the fact that more of them got 120s and 130s. Well, the people that had true IQs of 120 got lucky. They got a +5, right? Okay, hi. Sorry. The people that got a 125 test score, more of them are 120s than 130s. Well, the people that had a true IQ of 120, they got lucky. They got this +5 bonus, right? The people that had a true IQ of 130, they got unlucky. They got the -5 detraction from their score or subtraction from their score. So if you think about, are these people in this room kind of on average lucky or unlucky? Well, on average, they're lucky. On average, there are more people that got a +5 than there are people that got a -5. So they're not, the people in the room are not only smart, but on average, they're lucky. Next time they take the test, the luck kind of evens out. Half of them get +5, half of them get -5. No longer are these people lucky, right? Make sense, right? So when you take the 125s as a whole, more of them are +5s than -5s. When you take the second test, equal numbers of +5, -5. So that's one way you might think about why that average score goes down. Okay, questions on any of this regression effect stuff, this example? Okay, so I want to do one more conceptual thing. Okay. I guess a couple more conceptual things, sort of. I guess I'll erase that. Okay. So the next concept I want to mention is what's called the regression fallacy. Is the mistaken belief that it's the mistaken belief that there must be some other explanation for the phenomenon of the regression effect. So, the idea here is that if you didn't know anything about statistics, you didn't know anything about the regression effect, and then you observe this phenomenon, you observe that, Yao Ming's kids aren't as tall as he is. He must not be feeding them well, right? That's a mistake. That's a mistake, right? That's this mistaken belief that there must be some reason why his kids aren't as tall as him. So if you believe that, if you don't know anything about the regression effect and you don't anticipate this effect happening, you somehow expect Yao Ming's kids to be just as or sons to be just as tall as him, and then they're not. Some people will think, oh, there must be some explanation. They'll sort of search for reasons why something else, must be going on. So one example of this I like is a problem from the book. It's actually in chapter 11, but it refers to this idea. Chapter 11, review number 9. If you want to look at it, I'll just describe it, what the idea is. It has to do with the Rookie of the Year in baseball. So the Rookie of the Year, actually in baseball, I think is decided by sports writers. But let's suppose that the Rookie of the Year is decided based on batting average. So batting average is just basically what fraction of the times you hit the ball, okay? Roughly speaking. So good batting average means that you hit the ball a lot. Low batting average means you don't hit it so much. And let's suppose they give the Rookie of the Year award to whoever has the very highest, whoever sort of hits the best. very roughly speaking. Okay, so there's a phenomenon that people have observed that whoever gets the Rookie of the Year award tends to not do as well their second year, okay? So, they typically do well, but their batting average usually goes down the second year. So just write that. Has lower batting average. Second year. Some people have referred to this as a sophomore slump. Sophomore, meaning second year. They're typically, the Rookie of the Year will typically have their batting average go down. And some people have attempted to explain this in a variety of ways. Maybe they're like all cocky now and they think, oh, I'm doing great. And so they don't take it as seriously, they don't try as hard. Maybe the opposing pitchers study them and figure out what they're doing and know what pitches to throw against them that it won't be able to hit as well. There might be a variety of explanations for this. Maybe the pressure of being Rookie of the Year gets to them and they, there's all this publicity, whatever. They start going out with Jessica Simpson. I don't know. Anything could happen. So the Rookie of the Year typically has a lower batting average the second year. Okay, so how do we explain this? It could be the regression effect. So it's possible that there is some reason, right? And certainly in some cases you might, if you look at specific rookies, there might be reasons why their batting average goes down the second year. But in general, there's not really, such an explanation is not necessary as long as their behavior the second year is roughly what regression should predict, right? So if you have like all baseball players their first year and then look at their performance the second year, what you're talking about is some positive correlation, but not one. No one's going to do exactly, or you shouldn't expect everyone to do exactly the same both years. But you're talking about someone out here, right, the very edge. They're predicted to do well, but not as well. The person who does the best the second year may be, in here somewhere. Okay, and one way I sort of like to think about this is that there may be some small group of very talented baseball players that kind of might get the Rookie of the Year. Say there are 10 equally talented baseball players. One of them ends up with the best batting average, but maybe another one could have. So the one that ends up with the best batting average maybe gets a little bit lucky, maybe avoids injury, whatever goes into making a good batting average. Not only is this person talented, but whatever part that luck might play, that works for them, okay? The next year, maybe they get, this luck kind of evens out and someone else gets lucky, they don't get as lucky, okay? So that's one way to think about how the regression effect is working. Now, if this person did below average the second year, then that can't be explained by the regression effect. The regression effect should not make you go on the other side. As long as correlation is positive here, if you do well the first year, you should be predicted to do well the second year, just not quite as well. If you do poorly, you should be predicted to go up a little bit on average. Again, not everyone that won't happen to everyone, but on average, the people that are down here will tend to do a little bit better. Okay? So, questions about this? Regression fallacy? Okay. So, one more thing I wanted to talk about. Sort of tried to leave this picture here because I thought I might talk about it a little bit more. It's getting a little bit messy, so I'm going to redraw that picture, but you can sort of think about the same one. I don't want to draw the whole graph of averages and everything on it. So back to midterm and final scores. So the example I did, we started with midterm score here, final score here. And average midterm is 71. Up here is 83. And what I did was I found the average final score corresponding to these people. This point was 76.6. Okay? And roughly that should be very close to the regression line. Okay. So now I was saying, predicting back the other way, I did the calculation and found that for all the people that get a 76 on the final, I think their average midterm score should be somewhere around there. Okay, so this point should correspond to 75.3. Okay, and that's by my previous calculation. Okay, so you might not remember that, but I took this 76.6, multiplied by R, convert out of standard. Convert this to standard units, multiply by R, convert out of standard units, and I got 75.3. So you might think of that as roughly the average X value, the average midterm score corresponding to everyone who got a 76.6 on the final. Okay, so that point is not on this regression line that I've drawn here. It is, however, on a different line. And that line roughly goes like this. Okay? And again, I'm attempting to draw that line so that it goes through the average X value corresponding to each Y. So what's going on here is that there are two regression lines. So one predicts Y from X. And the other predicts X from Y. All right, so in the context of this problem, we have the one line that we started with that predicts final score from midterm score. And there is in there another line that predicts the midterm scores from the final scores. And it's not the same line. Okay. Now, whenever you're doing a problem where you want to predict one thing from another, my suggestion is that you just convert whatever you're predicting from, convert it into standard units, multiply by R, convert out of standard units. Just follow the regression method. I do want you to see, though, that there is this other line going on here, and it's not the same line, right? So you can't, like I said before, you can't go backwards. If 76.6 is the average Y value corresponding to that X value, it's not true that 83 is the average X value corresponding to this Y value. Okay, so this one predicts Y from X, and this one predicts X from Y. All right. If the correlation is 1, they're the same line, and all the points are on that line. If the correlation is 0, then the first one is very nearly horizontal, meaning that if correlation is 0, no matter what X value you get, you predict pretty much the same Y value, pretty close to the same Y value. And so if R is 0, then the other one's very close to vertical, kind of going back the same way. So if the correlation is pretty close, then those lines are pretty close. Sorry, if the correlation is close to 1, those lines are pretty close. If the correlation is close to 0, they're pretty far apart. Okay, there's one other thing I want to mention on this picture, which is, I sort of skipped over. It's in chapter 8, actually. It's section 8.3. It talks about the SD line. So if you notice in your book, you might notice that. The SD line is halfway in between these two. And I'll talk about it more when I talk about chapter 12. Okay? But I just thought I'd draw it in here since I'm drawing these other lines. The SD line is halfway in between. And it doesn't, it's not a very good line to make predictions from, but it kind of slices the picture in two. So geometrically, if you're drawing these pictures, I'll just tell you how I try to eyeball it. If you draw vertical tangents through your football, tangent line there, that first line should go through those points. And I guess I didn't do it so well here, but if I had a tangent line here, should go through those points. They both go through the point of averages. The SD line, sort of right on the seam of the football, if you want to think about it that way. If you folded it over, it would fold, symmetrically around the SD line. If you folded it around the regression line, the two halves wouldn't match up, okay? But the regression line does have this nice property that it roughly goes through the graph of averages, so you have the average y corresponding to each x. Okay? All right, so let you go. Thursday, I'll do chapter 11, which talks about how accurate regression is. So we've done this prediction process, sort of curious about how good the predictions are. Okay? Questions? Okay, yeah, question. We won't really use it. It's just, I just compared. Question is, what do you use the SD line for? I'll talk more about it later, but for now, not really anything.